let me just start. Okay, let me share the screen. Can you see? Can you see the screen? Is it visible?
Yes, I can see the
Yes.
screen.
All right. Okay. Wonderful. So let's start our next topic, which is of work, energy, and power. Right. Okay. So the goal is to understand all of these terms, these three terms, and then see how is these quantities related to each other, right? So understand what they mean, understand their relation as well to each other, right? And then we can talk about a very important principle in physics, which is known as the conservation of energy. And it is this principle, in fact, in this chapter, that if you understand this conservation of energy, this is a very important rule or principle of physics. If you understand this, then you can do more or less any problem in this chapter, right? So the most important thing is this principle of conservation of energy. And so, of course, then once we understand this conservation of energy, we can talk about different types of energies. We have kinetic energy that is related to the motion of the particles. We have the potential energy that the particles have in themselves, or you can do some work against some field, and this type of energy, which is the potential energy, develops inside a particle, or saying inside a particle is far-fetched, but anyways, right? So these are different types of energies that we'll be talking about. And then finally, we'll see that can I relate another physical quantity with energies, right? And that quantity is force, right? So I want to see that if force is related to work, energy, and power. So I just wrote W for work, E for energy, and P for power. So this is the goal that we have to complete in this chapter. And so we'll start with the topic of work, right? Now, I'm going to pick up the pace a bit, and you can let me know after the lecture if you're fine with this speed, right? As given the circumstances, we have to cover everything, and we're lacking behind right now due to some unfortunate circumstances. Okay, so work, you can think of work in multiple ways, right? But in physics, you have to assign a scientific definition to work. So the scientific definition to work is that if I apply a force on something, suppose that I have an object over here and I'm standing over here and I want to push this object. So I'm going to apply a force on this object. Applying the force does not mean that I'm doing any work as of yet. But if this force is responsible for the movement of the block, then I can say that some work has been done, right? Then we can talk about work, and that is work. That is simply work, right? So you can say that it is defined as when a force applied on an object moves its point of application. So by point of application, it just means that if that point where the force is applied, suppose that I apply the force on this point, and then when the block moves, obviously this point is going to move with it. And so the block is essentially moving, and when it moves in the direction of the force, right? So in the direction of the force, then I can say that work has been done. right? So what is the important thing? Important thing is that if a force is going to move an object in that direction where the force was applied, only then work is done, or you can talk about work, right? So the idea of work clear?
Yes, clear.
Yes. All right. So mathematically, then you can. There is a very a vectors and scalars mathematics algebra behind this, but I'll just quickly tell you that mathematically you can write this as F, and then there is it's basically multiplication, right? Multiplication times the displacement, where F is the force that I applied, and displacement S is the distance that it moved in the direction of the applied force. Now, we represent this thing with something that is known as a dot product. So I can write this F dot S. What this dot product essentially means is exactly what we talked in the definition. This type of a product assures that the directions of both the quantities that are being multiplied is the same, right? So I'll write it over here. This product ensures the same direction of both quantities that are being multiplied, right? Okay, so you can mathematically you can also write this as F, and then just F and S are two numbers. So take those two numbers and multiply those two numbers. They become F times S, Fs, right? And then the dot product comes out in the form of cos, and then there's this angle theta. This angle theta is the angle between these two physical quantities, meaning that suppose that I had a block like this, then I can apply a force to it. Suppose I can apply a force to it in this diagonal, and then the box will move. Suppose that it's constrained to move on this straight line. So there is only a particular amount of force that allowed this box to move in this line. And that, suppose if this is the force, that is the horizontal component of this force, right? So there are two components. This is the Fx component, this is the Fy component. And now you can see when we talked about components in our previous chapters, how that comes into the play over here, where Fx is simply, if you remember, it is F cos theta. What is theta? Theta is the angle between this force and this horizontal line, right? So it's this angle theta. Now, that's why work can be written in these two forms, either F times S or Fs cos theta. So if you're given some angle at which the force is applied, then you will plug that angle into this expression, and then you can find the work done. Now, quickly, let's discuss some of the cases, and that will you're going to answer for me what would be the work done in these cases. Would there be any work, or would there be no work in these particular cases, right? Suppose that I'm standing over here, and I have to push a block, right? We have a block over here, and suppose I apply a force in this direction, and the block moves in this direction. What can I say about work done? Will the work be done in this case, or will it not be done?
It will be done as there's a force and a distance moved.
There is a force, and the object moves some distance in the direction of that force, right? So
Yes.
we'll say that yes, work can be done in this particular case. Suppose that I have another case where I have this block, and I apply a force in this direction, but for some reason, because maybe for other forces that we are ignoring right now, the block is moving in this direction. Can I use these two quantities to multiply and get work done?
I don't think so.
We cannot, right? Because we have to make sure that the direction of the force and displacement is the same. But clearly, this is not same. And you can check that as well, because once you put these F and S, these are at 90 degrees to each other. You can put them in this expression, and then you'll see that this gives you work done as 0. There will be no work done in this particular case, right? So, because the directions of these quantities are not in the same line, right? And so we'll say that no work can be done. Is that clear for everyone?
Yes.
Yes.
All right. Okay, so let me give you one more example. Actually, it's the same as we have discussed. Suppose I apply a force to this object in the upwards direction, and the block is moving or moves in this direction. Will I say that work is done or it's not done?
It's done because the angle are the same. They are on the same line.
They're on the same line, so they are in the same direction. So I'll say that yes, work is done. So what we have learned is that for work to be done, force and displacement must be in the same direction. All right, so that's something that you have to remember. This is an important point. So that's when you can say that work is done. Now, we know we can talk about the units very quickly. We know that force is kilograms meters per second squared, or it is newtons, the units for force, and displacement, the units for displacements are meters. So when I combine these two units, as in F times S, it becomes, we are combining units, right? So I'm putting these brackets. So we get kilograms meters squared per second squared, which is also newtons times meters, and these are called joules, right? So the unit for work is joules. I think
Okay.
Joule.
Yes.
Right. Is there any question from anyone?
Yes, sir. Sir, uh, the unit for moment, sir, is also joules, sir. Is also Newton meter. So, is it considered as
Yes,
well?
yes, yes. Yes, yeah, you're absolutely right. But whenever we're talking in terms of energies, we use the unit joules. We don't use joule. We don't say that Newton meters is joules when we're talking in terms of moments or anything. So that's also a topic that we can discuss on. There is a form of you can say that there is a form of a relation, but all of those things then could be philosophically speaking. So at the moment, I'll not get into that. But of course, the units are same, but we know when we're talking about energies, and when we're talking about energies, then we say that the unit is joules, right?
Yes, sir. Thank you, sir.
Okay, okay, wonderful. So clearly, hopefully that you can see that work done itself is a scalar quantity. Everybody agrees with that?
Yes.
Okay, great. So all right, so that's more or less work. Now let me go back to this formula. I'm going to should I do that, or should I don't know. What I'm saying is that sometimes it's better to write down the formula for work done as force times displacement, and then put brackets and put a parallel sign like this. This sign means that the it's a sign for symbol for parallel. And what that means is that just makes you'll just remember that force and displacement should be in the same line, right? So you'll never so that you don't forget for work to be a non-zero number, it has to be like this, parallel to each other. Now there are two types of or you can that's why we also have the symbol F dot S, but I think at this point you will not be familiar with the dot product, and so it's useless to get into that. So that's why I'm just using this parallel symbol, right? So if you write your formula like this, then you'll always remember the conceptual part of work done as well. Anyways, so there are three things that we have, at least one thing that you know, that if these quantities F is perpendicular to S, then no work is done. Because in that case, the direction is obviously not the same at all, and completely there will be no work that is done. But we know, as I gave you an example, that suppose if you have a case and it's not perpendicular or either parallel, these two directions, F or S, but S has a component that is in the same direction as S, which is the Fx component, while Fy component will contribute nothing to the work done in displacing the block in S direction. However, Fx at least contributes something in moving the block in this S direction because they are in the same direction. And then we can say that we have to be careful when we are looking at problems. We have to consider the components of the force as well. Is that clear?
Yes, clear.
Yes,
All
sir.
right. So now let's talk about these sign conventions very quickly. Sign conventions for work done, which essentially means that when do I say that work is done by this force, or is the work done against this force? This force के खिलाफ work करना, right? So so when we say that if I apply a force to a body and the body is moving in the direction of that force, then I take positive work, right? Positive work is when force applied is exactly in the direction of motion. Direction of S, right? S is the displacement. And it is taken to be negative when if I apply F and it is opposite, exactly opposite to the direction of the motion. So now you should not be confused. There's one more term that we use for this positive. We say that force did the work. And you can imagine the situation. If a force is pushing an object in the direction where I want this object to move, so if take a book and push it in some direction, you want it to move in that direction. So you're saying that this is a positive thing happening, and it's something that you want to happen. So you say that work is done by the force, work done by the force. But if I'm applying a force to an object, but somehow yet due to other external forces, it is moving exactly in the opposite direction of that force, in this case, everything is negative. You don't want this to happen. So the work is being done against this force. So there are these other forces that are doing work against what you want to do. And in that case, you say that the work done is negative. So we can say that this is work done against the force F. All right. So is that clear?
Yes,
Yes,
clear.
sir.
Okay. Everyone is following along?
Yes, I'm following.
Yes. All right. Okay, good. So now let's move on to the next topic, which is, well, obviously it is still, we are still in the regime of work done, and we'll talk about gravity and work, right? How are these related? Gravity and work. So it's very simple. Again, we can think of gravity as a force. We think of gravity as a force, and it's a force that acts always directly to the center of the Earth. Saying that it acts directly downwards can be wrong. So we say that it acts directly towards the center of the Earth. It just appears that it's always downwards, right? If you're standing on the surface of the Earth, because I hope that everyone agrees that Earth is not flat, it's spherical. And so it's towards the center of that sphere, and it appears that it's always downwards. So if suppose that I have an apple, and this apple is falling downwards. You tell me, is the work done by this force of gravity positive or negative?
Positive, as the
Positive.
force.
Because
Yes,
it's in the same direction as the force.
wonderful, right? So both of you are correct. It is because the apple is moving in the direction of the force of gravity, right? Because whenever there is this acceleration due to gravity, this is just the force of gravity, and the displacement of this apple and the force of gravity are in the same direction, and hence the work done from this scenario is positive. All right. And obviously, suppose that if I lift an apple in the other direction, suppose that if I lift the apple in this way, right? You can think of that it's lying on the ground, but I'm lifting it upwards, and we know that the force of gravity is still in this direction. So clearly, in this case, the work done is
Negative.
negative, right? So it's negative. And now, hopefully, you will not be confused with what sign should I use and what does that signature with the work done means, right? So if it's positive 10 joules, then what does that mean? If it's negative 10 joules, what does that physically means, right? Okay. So then we can say now that work is done against gravity, right? If an object rises upwards, and work is done by the gravity if the object falls to the center of the Earth. All right. And now there's another example, which is an example of, let me rearrange these things as well. So there's an example of another force that always does work against that force. Can you give me an example of a force?
Frictional.
Amazing, right? So yes, exactly. So frictional force is a force that always tries to stop the motion of an object or the flow of an object. It restricts that motion. And so because an object, maybe it's trying to move in a direction, frictional force is going to always oppose this movement. And so the work then will always be negative. Right? So that's how work done and friction are related. Right? And so let me just... So everyone is following along. Is this clear for everyone?
Yes, clear.
Okay, good. So now let's do an example, right? And okay. From here, this will lead us to different types of energies. Let's think of an inclined plane, right? Let's do a problem. We have an inclined plane, right? And suppose that I have anything, an object, let's consider a bowling ball, and it's resting at the top of this inclined plane. Eventually, I let this go and the ball rolls downward and reaches this point over here, right? Suppose that initially the height of the ball is anything 5 meters or centimeters, and if that is the case, I want you to tell, and also suppose that if this length is around 12 centimeters, if I were to calculate the work that is done by the gravity comes from this weight of the ball, right? And suppose that there is this friction between the ball and the surface, and that is the frictional force F, and maybe it is anything from 50 newtons, right? And this length is 13 centimeters. So the distance that it travels downwards is 13 centimeters. How about you tell me, if I were to calculate the work done by gravity, what force and what displacement shall I use? We know that work done is a force times displacement, right? This is the formula that we are familiar with now. I want you to tell me that I forgot to write down the weight of this ball. Suppose it's 100 newtons. If I were to calculate work done by gravity, which force and which displacement shall I use? Anyone?
Uh,
50 times 100.
no.
Okay, 50.
Uh,
Remember that this is the frictional force, right? Yes, Taha or Muiz, you're saying?
Yes, we will use 100 as force, and we will use the angle as well, and the distance move, or s.
The distance for S.
Yes.
Right. So you're saying that we'll write this as F S cos theta, and then use this angle. But think about this. Weight is downwards, and it's moving in this
Is it
direction.
gonna be 0? Because
No. Taha, or if it was Taha or Muiz, they're in the right direction. So think about this. Remember, you have to remember that the only force that contributes is the force that that is in the direction of the displacement, right? But
So it is negative. So it's negative because only force that is on the same line is friction.
no, you know that the ball is moving downwards, right?
Yes.
It's moving downwards. We don't have to use the angle, and the reason for that is we know that weight is always downwards, right? Weight is going to be always downwards, and this distance that we are given, this one, it is the downwards distance as well, which is 5 centimeters. This is also downwards. So the work that gravity is doing is moving the ball downwards, but only that component of the displacement is being used, which is in the direction of the weight. So the
Yes.
displacement that we require is this one, right?
Yes.
Okay, good. So it's clear for Hassan, I think Hassan, and everyone else as well.
Yes, it is clear.
Yes, sir.
Okay, good. Is everyone following along? How many people do we have? Let
yeah,
me.
so
Okay. Noor, are you following along?
Yes, sir.
How about you, Urva? Are you also things are clear?
Yes.
How about you, Had? Had, if I'm
Yes.
pronouncing your name right. It's clear. Okay. Okay. Good. Good. So gravity. So the work done by gravity in this case would simply be F times the displacement or the distance that is directly downwards. F is the force of it's the weight of the ball. So it is W times 5 centimeters, where W is 100 newtons, and will of course convert centimeters to meters, and this will be 0.05 meters and 1 2, so this becomes 5 joules, and it's a positive number, so the work done by gravity, and so the work is done by the gravity, right? The work is the gravity is doing some work to basically move the ball downwards. So gravity is only doing 5 joules amount of work. Let's compare that with another force that we have in this example, and that other force is
Friction.
it's friction, right? So the let's find out the work done by friction. Let me see how much time do we have left in this meeting.
4
Okay,
minute
4 minutes.
23.
Right. Okay. So can anyone do me a favor? Just one person who can always let me know when it says less than 1 minute remaining, right? So
Okay,
I
I will
really
let you know.
appreciate that. As soon as it says less than 1 minute remaining, just let me know, right?
Okay.
Okay, good. So a work done by friction is going to be what? Of course, we'll use the force that is the force of friction. The question is, what displacement shall I use in this case? Can anyone suggest? We are trying to compute the work done by the frictional force, and this is the frictional force.
Is it 13 and we will just 13 centimeters?
13 centimeters. All right. So the displacement. So you're absolutely right with the numbers, right? So the force is the frictional force, which is 50 newtons. And because you can see that these directions are almost the same, except for the fact that they're in the opposite lines, right? But they lie on the same line, but in opposite directions, in exactly opposite directions. So there should be a negative signature added before anything that we do. And now
Yes.
we'll multiply this with 13 centimeters in meters. That would be 0.13 meters. And this would give you negative 6.5 joules.
So this is negative work.
Negative work. So it's the work done against this frictional force, right? And unfortunately, the frictional force does not win, and the ball eventually slides downwards to in the slope.
Yes.
So
Sir?
is that yeah, sure. Go ahead.
So, work, you said that work is a scalar, right?
Work is a scalar, yes.
Okay, but then why is it negative, sir?
Oh, it doesn't matter. Any number can be negative, whether it's a scalar or a vector. It does not. That does not mean a scalar does not mean that a number cannot be negative. All real numbers are scalars, right? So you know that with all real numbers, they have positive numbers, they have negative numbers as well, and they have a zero in them as well. So these are scalars. A vector is something that has a magnitude and the direction is associated to it as well.
Yes, sir.
And so, I mean, if you think of only this definition, then it's confusing, because you might say that in this case, work done if I say that it's positive, then it's telling me something else. If I say negative, then it's
Teacher,
telling me
it is
something
less than
else,
1 minute, less than 1 minute.
Less than 1 minute left. Okay, so all right, but still, you have to go into a deeper definition of what is a vector and what is a scalar. And that definition is in mathematics, right? So it comes from mathematics, and in fact, it comes from group theory and all of those things, vector spaces. And so I cannot go into that right now, but for now, you'll have to take this for a fact that work done is a scalar, even though it's confusing. And it's confusing because this definition that you are all being told that scalar is just a number, while a vector is a number with